21ª Cátedra Europa, el encuentro académico y cultural del Caribe colombiano y el mundo académico europeo. Europa se vive en el Caribe.
Buenas tardes, and thank you so much for having me here. I'm a very visual person. I love teaching students, and so I've already got my props ready to teach here today. So if you'll bear with me. So my subject is forward, the top button, this one. Okay. So Oscar, I really appreciate the intro into my speech because some of the questions that came up in the last speech are demonstrated in this slide here. You've got the side that does not want hydraulic fracturing, and you have the other side that does want hydraulic fracturing. So hopefully I can address some of the comments and questions that came up in the previous presentation. So today we're going to talk about what is fracturing and why do we do it. A little bit about rock mechanics so you can understand about addressing the exact question that came up. Do these fractures grow all the way up from the formation to the aquifers? And the answer is no, and I'll show you some actual data to prove that's not correct. What is the current state of the art of fracturing, which you would apply here in Colombia in your unconventional reservoirs? What is your potential here, which was addressed in the previous presentation? What does it cost? What is it going to take to do that? And finally, a little bit about petroleum engineering at Texas Tech. So what is hydraulic fracturing? First off, you're pumping water and sand at very high rates and pressures into the rock to create a fracture, a crack. Then you place sand, like you have on your beaches here, into that crack to keep the crack from closing. We oftentimes, in some reservoirs in West Texas, which is where I'm from, pump acid that you use in your pool. Muriatic acid, hydrochloric acid, same acid you use in the pool to keep it clear and clean. We use that. It reacts with the limestone, if you have a limestone reservoir, to actually react with the rock and make paths for the fluid to flow. So why do we do it? Number one is bypass damage caused by drilling the well, and moreover, stimulation. These reservoirs do not conduct or allow fluids to move in them very well. They're very low permeability, or we call them tight. So what do? We drill a well, and these are some videos I'll leave with you. Then we construct a well bore that is going to prohibit fluids from migrating from the formation up to freshwater aquifers. We use steel pipe we call casing, and then surround that casing with cement. So the steel pipe and cement are placed at a depth just below the aquifer. And in Texas, we have the exact same rules that you have here in Colombia. I was noticing that there is a requirement in Colombia about the depth that you place this pipe and cement relative to where the aquifer is found. So we have the exact same rules just where I live and where you live in Colombia. Then the well is continued to drill further down to the formation that you're interested in producing oil or gas. And then we run more steel pipe and surround and fill the area between the steel pipe and the hole that you've drilled with cement. And the cement is meant to contain fluids from migrating here, up to here, and up to your freshwater zone. So again, fracturing. So this is where I get to use my visuals a little bit. So you see here in the first well, these are conventional wells that we've been hydraulic fracturing since the 1940s. We pump fluids at high pressures, water, mixed with sand to create a crack, and then we follow that water with sand to fill the crack with the sand particles we call proppant. So if I move your university flag just a little bit, so the flagpole represents the wellbore that you see there. As you pump through holes that we call perforations in the pipe, say here, we create a fracture that looks something like this. Okay, it actually extends both sides from the wellbore. And the fracture this is about relative to the size of the fracture to the pipe. So the fractures are very, very small cracks made with the fluid. Some vision, they show hydraulic fracturing as blowing up the earth, like we've ignited something downhole that actually shatters the rock in all directions, which is absolutely not true. You're pumping fluid, that's why we call it hydraulic fracturing, to create the pressure to allow those cracks to happen. Again, what kind of fluid are we using? Most of it, over 99% of the fluid is pure water. The bulk of the remaining portion is a plant called guar. It makes a polymer. So we're basically pumping water and plants downhole. So the amount of chemicals used, most of it, which is very non-reactive, are basically infinitesimal. The dangers are earthquakes. But oddly enough, people associate fracturing with the fact, this concept we're blowing up something downhole that causes earthquakes, which is simply not true at all. The hydraulic fracturing treatments are not creating earthquakes. What does create earthquakes is exactly what Oscar just told you, and that's injecting that water that we just injected into the well to create the fracture. We have to flow that water back and get rid of it, because it does have contaminants from the formation, mostly salt water. We don't want to dump salt water in our rivers, streams, or on the ground. So what we do with the water is inject it back into the earth, into a zone that typically does not contain hydrocarbons. It contains salt water. So we're injecting salt water into a zone that contains salt water. Now, if that injection happens near an active fault, as you saw a few slides ago from Oscar's presentation, it can induce an earthquake. So we've mitigated that by simply moving the injectors far away from active fault zones. In fact, in Texas, you have to actually do a seismicity survey within 100 square miles of the well that you're proposing to inject water into to ensure that that doesn't happen. This is near my home, where I live, so I believe in it. My water that I drink in my house comes from well water. So what we say in the U.S., I practice what I say, what I speak. So this is near my home. These are injection pumps injecting water into this well here. And it's injected into a formation that already contains salt water, and it's governed by almost the exact same rules that you have here in Colombia. So let's talk a little bit about rock mechanics. So why do I say that these fractures cannot grow up into our freshwater zones? So first off, these fractures are not as simple as we initially thought. Instead of looking like one plane, if I were to look at this is me looking from the surface down. So I'm looking down on the plane of the fracture. We initially thought that the fractures were two single planes like this. And moreover, in the conventional reservoirs, they were like this. But more in the unconventional reservoirs, the rock is already fractured. Mother Nature has already fractured the rock for us to some extent, and the fluid finds these paths in these unconventional reservoirs that have fractures. Now, if I was to look at this fracture from the side, So now instead of looking down on it, I'm looking at the frack here. These fractures, instead of looking like this, look like this here. And to make it even more complex, we have to place sand, and it has to say suspended, because if it does not, the fracture closes back, and it's just like it was before. It becomes useless to us and does not conduct any fluids. So, can fractures grow to the surface? Only if we fracture very shallow. But simple rock mechanics is that the rock is going to part in a direction that is easiest to push away. So I have two large trucks pushing on either side of me, and then if I have two small motorcycles pushing this way, the motorcycles are the easiest to push back as opposed to the truck. So that's what happens with earth stresses. This would be the truck. This would be the truck here. This is our maximum force. And this would be the small motorcycle. Obviously, it's easiest to push in that direction. So the fracture is going to grow towards me as far as relative to that screen there. Now, if we fracture wells shallow, then the actual least force is the vertical force, and these fractures actually grow in a flat plane. I'm not going to go through the equations here, but we can predict those pressures it takes to part the rock. These are our modern day, state-of-the-art horizontal wells and unconventional plays. We like to drill a well with the horizontal portion where when we do the hydraulic fracture treatments, the fracture plane here is perpendicular to our horizontal well. So if I'm drilling my horizontal well this way, we like the fracture planes to look like this, not like this. So that is part of the technology we've researched at Texas Tech. Which way should you drill the horizontal well? Now, to address how these fractures grow, here are two wells drilled in the Eagle Ford near San Antonio, Texas. You can see that they're very close to one another, and we actually can put downhole phones and more or less hear and triangulate where the fracture is growing. So you can see here that the fracture in vertical grows very little. It's only growing probably 10 to 40 meters at most. It is not growing above this zone here. And that's because of rock mechanics. It's simply put, any change in lithology and the mechanics of the rock will alter or stop the fracture from growing. Same thing on the width-wise. You can see that these wells are not very far apart. This well here is this line. This well is this line. And you can see the fractures did not grow very far out from this horizontal well here. Moreover, we have also drilled into and mined after fracking the well. Here are two coal wells, that coal bed methane, which I just learned that you have coal in this country, a lot of it, in this near this region. And these are wells, we produce the gas from the coals, and we wanted to see how much these fractures actually grew after the job. So we pumped the hydraulic fracture treatment after drilling these wells, and then actually mined to the well so we could actually visually go down in the well and see the fracture as it formed. And you can see this is less than 1/3 of a meter is stop of different type of rock has stopped this fracture from growing up. And that's only 1/3 of a meter. You're talking about something like this. Same thing here, same thing here. Here is an example of a mined product that we've had this rock that we have this bedding plane that's only a few centimeters that has stopped the fracture from growing up. So this is how we know, both from the mechanical properties of the rock and actual data we collected, these fractures don't continue to propagate up and up and up. So real quick, how are these done? You already saw the horizontal wells here. We drilled them roughly 3,000 meters down and roughly 1,500 to 2,000 meters horizontally. We perforate, we pump the water, just like I showed you in the vertical well, into these perforations, carrying sand and proppant that looks like this. This is a blow up of this zone here. So you can see where we've placed these sand particles. And then once we release the pressure and quit pumping, this fracture here that you can see that's 0.1 inches closes. So the fracture closes on top of the sand. The sand keeps the fracture from totally closing together. So the concern that most have is that, is the sand strong enough to not crush when the fracture closes? So this is one of the big concerns I heard from Oscar in the previous presentation. You got to have this sand and lots of it to perform these hydraulic fracture treatments. So the sand is at the bottom. In the U.S. is $25 a ton to mine and produce ready for market. These expensive proppants made in China and the U.S. are roughly $200 per ton. So you would rather use this if you can. But you certainly, and I don't know this, need to find a source of this sand here in Colombia. It's extremely important for you to be successful in hydraulic fracturing. Then again, this is next to my home in Lubbock, Texas. In fact, this is my pickup truck. After you finish drilling the well and doing your fracturing treatment, you place it on production. Most of the wells won't flow naturally, and we have to put pumping units on them. Some will flow naturally for a while, not needing artificial lift. So what does a frac job look like? So again, this is near my home. This is a frac job on a well that's located just off the screen here. I'll show you in a minute. But you can see all this equipment after the fracture treatments goes away, and there's nothing. It looks kind of like out here, just desert. This is actually, sometimes we add carbon dioxide to energize the frac to make it easier for the fluids to flow out. We fracture treat 24 hours a day. It's a nonstop manufacturing process. In fact, this is my daughter, who graduated from Texas Tech, is an industrial engineer. It was hired by Anadarko, who has your offshore leases out here. And her job is to optimize all this equipment movement and procedures, what happens. So you that are industrial engineers, there's a lot of opportunity for it here, because this is more of a manufacturing process as is a petroleum engineering process. We fracture on the North Slope in Alaska. Actually, this is a frac job being done in north of Alaska. Some issues or hazards you might not think of is the silica dust that is generated moving the sand to the blender to pump downhole, and we have to wear protective equipment. Refueling, as I said before, this is a 24-hour operation that may last 5 to 10 days of nonstop fracturing. So we have to refuel these trucks on a continuous basis. One of the biggest hazards we have is refueling the vehicles. You saw this slide a minute ago from Oscar's presentation. I'm going to zoom in on your country. In the Magdalena River Valley here, in the Middle Mag, you have a tremendous resource of unconventional oil. I also learned that you have coal bed methane here, which I've worked on substantially back in the U.S. Both, a lot of potential for this country, a lot of jobs, and a lot of resources. In fact, he said that your resource or your reserves were 1.8 billion barrels for Colombia at this time. This Energy Information Association or administration in the U.S. In conjunction of a research firm, estimates in the Middle Magdalena alone, you have almost 4.6 billion barrels of potential resources. You could almost quadruple the country's resources in just developing up the Middle Mag. You also have the Llanos Basin that has potential. So what does it cost? What does it take to do this? So this is a typical frack site, again, near my home. These are all the high-pressure pump trucks that take the fluid and boost it up to several thousands of pounds to go down hole to actually create the pressure enough to part the rock. Before that, we have blenders. This blends the gels, the polymers, the sand, the water together to get ready to be pumped into the hole. By the way, this is the wellbore here. Here are your sand trucks here that have brought in your proppant. These are all water trucks here. This is called a data van over here. And you have miscellaneous sundry equipment all the way around here, chemical trucks and things of that nature. Just to show you how much has grown in the U.S., we are currently growing at a rate of 3.3 million hydraulic horsepower a year. That amount is more than all of the hydraulic fracturing horsepower prior to 2006 in the entire U.S. Sand, this is that other issue that you have to worry with. You can see the rapid growth. In the U.S., we're having concerns of where are we going to continually get this amount of sand. In one job, we pump these jobs at 100 barrels per minute. That's 16 cubic meters per minute. We pump 50,000 pounds of sand in 3 minutes. A job, 10,000 pounds of sand in just one frack job. So you can see the demand is quite high for these proppants. What does it take to put one of these fleets together? When I say a fleet, I'm referring to this here. This entire group of vehicles here is called a frack fleet. Well, the prehydration unit that hydrates the polymers, you're looking at $1 million. The chemical mixing trucks, about $1 million. The blenders, you need many of those on location to blend all those fluids and sand. Those are almost $1 million a piece. Each one of these high pressure pumps with a tractor trailer attached to it is $1.25 million US. And you put all that together, of course you got a data van that looks something like what you would see in a Star Trek movie or something of that nature. And you put all that together and you're looking at something from 40 to 50 million US dollars to put together just one fleet. Then you add to that, you're going to have to maintain that fleet. To maintain it, you need a facility and you need people. And I heard Oscar say, and he's correct, for one fleet, you need roughly 80 to 100 people to support just one fleet. And just to repair a fluid end, well, what's a fluid end? A fluid end is the high pressure end of that pump right there. Okay, just repairing that is $60,000 US. And finally, you've got to get all this equipment and sand to location. And when we do these jobs, we not only have to drive all this equipment to the site that you saw before, but you're continually servicing that frack fleet over multiple days. 5 days, food, sand, fuel, all that has to be continually supplied to that site on a 24-hour basis over 5 to 10 days, depending on how much sand you're going to pump. So how was Texas Tech involved in this? We were rated number 4 in the U.S. as far as best undergraduate petroleum engineering programs, number 9, and we're doing something about that number 9 to move it up. We're actually a relatively new PhD program, only since the 1990s, but we're growing rapidly. We have 70 graduate students currently enrolled, which is quite healthy, and roughly 400 undergraduate students. I'm a believer in visualization, so we use a lot of visualization equipment. So here is a pumping unit where I show the students how it is operating below the surface. So there would be what you would see at the surface, and then this is moving a little bit slow. And then this is, sorry I couldn't show you the rest. I don't show why the video didn't flow, but this is what fluids look like flowing in a horizontal well. And that poses this turbulent flow that you see in the curve here poses lots of problems for pumping the liquids. So there's a lot of research we're doing around that. We're looking at tubular strengths in here. I mean, how do pressures affect your tubulars downhole, and how to design around that. How to design your surface facilities and handle heavy crude. I understand you have a lot of heavy crude in the Llanos Basin. You're trying to pump it a long way to market. How do you go about doing that? And then again, how do you design these facilities to handle all the production at the surface? We actually have a facility at Texas Tech that's 5 minutes from campus that we can replicate the oil field. So all this equipment is exact same equipment you'd have in the oil field, but it's on our campus. This is just another view of it. Some of the research is done. This is, again, moving heavy oil through pipelines. Understand that that's a big issue. Cement, I mentioned cement is that barrier that keeps fluid from migrating. So we're investigating different types of cements and the strength needed for that. So sometimes we actually over-design on the cement. We have better cement that's lighter weight to place in the well that could do even a better job, but our current technology says that it's not good enough, and the current technology is not based by a lot of science. So I think we can do a lot better there. We're looking at improving the recovery from these shales. So in your country, you have a lot of enhanced oil recovery projects, improved oil recovery projects where you're injecting water to push the oil through. We're looking at, well, how do you do this in shale? So we had a lot of work at Texas Tech looking at how do we increase the recovery. Because believe it or not, in these shale wells, even they're extremely commercial and very profitable in the U.S., we're still only recovering 5%, 5 to 10% of the oil in place. So we're getting a very small amount out. So how do we get more? And that's what this research is all about. So with that, I'll end my presentations, and I guess I have a few minutes for questions. Okay, back over here. And I may need a translator.
Hi, good afternoon. Here.
Okay.
Have you ever considered about using other type of fluids, such as liquefied propane or similar?
Yes, and in fact, the one slide I showed you, we were using CO2. But believe it or not, water, which you're blessed in this country that you have a tremendous amount of water. In West Texas, it's basically a desert. We have very little water. Water is very precious to us in West Texas. So it's amazing these oil companies are, without regulation, or themselves are actually recycling this water, and they're looking to Texas Tech to provide research. How do we take this water, instead of injecting it into this disposal well, let's just clean it up and use it again. And we're doing that, and providing that technology. The funny part is that you think, well, what is the concern with it? And actually it's no concern mixing with the guar and the gels, but it does cause an issue in the reservoir. It mixes with the water in the reservoir and creates concentration of certain minerals that deposit scale, like gypsum or calcite, which I don't know if you have hard water in Colombia, we have it in Lubbock. So all our pipes in our homes, it's very hard water there, we have scale forming all over our pipes. So obviously that's 2 miles, 4 kilometers down, and that's very difficult to deal with if it forms those scales. That's probably our major obstacle.
Good afternoon. My question is about the equipment that you were talking about and the reservoir that you spoke about that is located in the middle Magdalena, right?
Yes.
That is the bigger one in Colombia, if I'm not mistaken, right?
Yes.
That was 4.6 or 4.8 billion
Barrels,
tanks, right?
correct.
Barrels, exactly. Yeah. The question that I have is, do you do you think that is a problem? The location and the geography, the topography that is surrounding that area that the reservoir is located in the middle mark, and how do you think that that problem could be addressed, where when Colombia doesn't have all the technology and equipment that you talk about that is necessary to, exploit that reservoir?
Well, first off, I mean, I think certain Colombia is capable of acquiring that technology. As I said before, it's more of a matter of acquiring the equipment and the pumping material. I mean, the pumping material is not new technology. What's new is simply combining horizontal drilling with fracturing, which has been around since 1940. So it's just a sheer volume. So the key is logistics, logistics, logistics. And you certainly need rail. I mean, that's what when in West Texas, I have friends that have actually made quite a bit of money putting in just a station by a railway to receive all this proppant, this sand. In fact, we just found a resource in West Texas of sand. So that's probably your most difficult product to get to the frac site is all this sand. The rest of it, can get through. In West Texas, we have pretty rough roads. I mean, we have a lot of roads we go down are dirt or what we call caliche. But that's not that big of an issue. But the issue of the continuous supplying over 24 hours is an issue, and moving that quantity of sand. Because the way you actually get the cost of these wells down, as they've done in West Texas, they've got the break-even cost from $80 down to $40. And the way they've done that is industrial engineers. How do we improve this manufacturing process? It's just like the Ford deal, the assembly line. How do we get it to assembly line and make everything happen very quickly? And if you break it up and do things slowly, that's going to hurt the economics. So rail systems, the Magdalena River, I don't know if it's a shallow river or deep river. I don't know the potential of actually using it for actual shipping up and down the river or not. And I've worked in Colombia, but from a reservoir standpoint. This is actually my first visit to Colombia. And by the way, I've enjoyed it. I brought my wife, and we've enjoyed it very much. And we'd like to come back.
Thanks a lot for your presentation. My question probably is not related to the technical issues, more complex in the way that I was wondering if the university itself involves in the way the government communicates the fracking projects, and if it does, what is that sort of communication channel or way to do it?
Well, I mean, if you're speaking to the environmental risk around fracturing, I think that the universities are greatly involved in that. I just mentioned the cementing research I'm doing for wellbore integrity, to studying the rock mechanics to show that these fractures, it only takes 2 centimeters of rock to actually stop the fracturing. This type of research is actually going on at Texas Tech now. Beyond just the research, we're training students at the undergraduate and master's level to understand and be able to design these types of treatments and whatnot. So, I mean, I would invite and would love to see some of all these smart students come up to Texas Tech and get masters and PhDs and become experts at this type of technology, and come back to Colombia and apply that. Along with, you and I were talking about coal bed methane. We can also train in that. I think I'm excited about that as much as I am this. I mean, you have a tremendous potential of coal bed methane in this country. Thank you.
21ª Cátedra Europa, el encuentro académico y cultural del Caribe colombiano y el mundo académico europeo. Europa se vive en el Caribe.